So I'm Katie. My Twitter handle is Katie_Fenn, but you can find me on Blue Sky now at Katie Fenn. And a content warning: this talk contains loud electronic music. So I'm Katie, and I really like Daft Punk, but you don't have to like Daft Punk to watch this talk. I promise. This talk isn't really about Daft Punk. It's more about the technology of electronic music and a whirlwind tour of what the Web Audio API and what the Web MIDI API is capable of, and a reflection on what the web is for towards the end. So just in case you don't know who Daft Punk are, they're a Grammy Award-winning electronic music duo from Paris, and they're famous for dressing as robots while performing. And this is the image that perhaps most people are familiar with. But what many people don't know is that their career spans nearly 30 years. They were pioneers of French house music, and this is the image that they selected for their first album in 1997. Early on in their career, they used synthesizers that were already old hat in the 90s, including a Roland TR-909 drum machine, which you can see here. This was released in 1983. And the Roland Juno 106, which was released in 1984. These machines could be found for under £100 secondhand, and this was because they were considered old technology at the time. They were considered passé. But they did have one new technology which would change the world of electronic music forever, and that technology was MIDI. This is what MIDI cables and ports look like. Nearly all synthesizers have them now, and MIDI cables are very cheap and they're very easy to use. MIDI lets musicians synchronize machines of different types and brands together. You could prepare performances at home on your sequencer and then mix them into a live performance on your MIDI-enabled synthesizer and drum machine in a club. Synthesizers were a common sight in prog rock bands in the 70s, and slowly they went from being a small part in a bigger band to being the band. Bands like Kraftwerk, Pet Shop Boys, Erasure, Orbital, Chemical Brothers, The Prodigy, and Daft Punk all used synthesizers to change the way that music was made and performed. And now the Web Audio API and the Web MIDI API integrate analog synthesis and MIDI into the web. These APIs are mere footnotes compared to our everyday work if you do front-end development, but they are very powerful, they're very creative, and they're a lot of fun to use. So let's explore these technologies, and let's make a full song. Let's make Daft Punk's 1997 single, Around the World. For those of you who are watching now, this is what it sounds like. So where do we start? Let's start with this. This is my Arturia KeepStep Pro. This is the thing that you can't see. It's out of frame. It's on my desk here. This is a MIDI controller and a sequencer. It looks a little bit like a keyboard, like you'd have in your bedroom to make music on in the 80s and 90s, but it's slightly different. This makes absolutely no sound of its own. It only sends MIDI data to my computer. MIDI data tells computers, synthesizers, drum machines which notes to play. MIDI data can even be used to control lighting and visual effects in a live performance, and that really goes to show that MIDI is about message passing and nothing else. So let's hook this up to our browser using the Web MIDI API, and then we can see what MIDI data looks like. So I'm going to be using just normal Chrome DevTools, and the sources, I'm trying to get to the sources panel, but it's right behind my screen sharing controls, helpfully. So I'm going to move those out of the way because I don't want to drop off the stream. Okay, so we are looking at this. Okay, so I'm going to try and get some MIDI data into my slides. And the first thing that I'm going to do is I'm going to get the MIDI. I'm going to try and get the MIDI access from the navigator. And this is like the gateway to all the MIDI API. So I'm going to type let access equals navigator dot request MIDI access, and we're going to await that as well because it returns promise. Next, we're going to iterate through all the connected devices. I've only got one device connected, but if you have a big home studio, you might have more. So we need to iterate through them. So we're going to iterate through device of access.inputs.values. And this is just an array, and it's going to return to us all the devices. Then if we have device.name of KeyStep Pro, then what we're going to do is we're going to create a callback which gets a callback function which gets executed every time that I push a key down or I turn a control or change anything on here. So we're going to set device.on MIDI message equals to a new callback. And that gets a variable passed in with the MIDI message. So we're going to call that message. Next, because message, the message variable which gets passed in, is an unsigned integer 8 array, we want to turn that into a normal array so we get the access to all the normal array API methods that we can use to start manipulating that array. So we're going to create a new variable called data, and we're going to use array.from to create a new normal array. And then what I want to do is I'm going to use document.query selector. And I want to get this, an element of this class here. And then I'm going to set inner text equal to message.data.slice. So I just want the first 3 items of the MIDI message. And hopefully, if I run that, I might need to open the console just to keep an eye on any errors that get turned up. Okay, let's see if this works. Fantastic. Okay, so we can see some MIDI data here. Let's see what this looks like, and I'll tell you what each bit is. The first value is the status byte, and it's often used to identify the control that's being pressed. So if I press one key down, then we get 146. Some controls have different values depending on their context. So if I lift the key back up again, we should get a different number. So we get 130. So 146, 130. Or 153 and 137 if I'm on the right setting here. So this has context, and depending on the control that you are using, it might return one value or the other. The second is the data byte, which carries information such as the note that's being pressed. So if I press bottom C, then we get 36. If I go up a semitone, then we get 37. 38, 39, 40, 41, and so on. Additional parameters then follow, and here it's the velocity of the key that I'm pressing. And velocity, what that means is that if I press a key very slowly, then I get a very low number. And if I push it very fast, then I get a very high number. And you can use this to write your code to accentuate or quieten some of the sounds that you want to make, like a real life piano would. When you push one of the keys down very hard, you get a much louder, brighter sound. So that's what velocity is for. Or if you move some of the, let's see, if I move some of the other controls on here, then we might get a number which goes up and down. Okay, so the brilliant thing about MIDI data is that you don't need API documentation to use these values. And weirdly, counterintuitively, it makes them easier to understand. They're designed to be used to be learned intuitively, and professional audio software works the same way. So if I wanted to hook this um, uh, MIDI controller up to a professional digital audio workstation like Logic Pro or Ableton, I would set the setting that I'd want some of these controls to change. I'd put it into a learning mode, then the next control that I would move will get assigned to that. And you write your code in the same way. Counterintuitively, this means that you don't need any API documentation to learn how each different thing, each different device works. As long as you perform the same action in the same way twice, you'll get the same MIDI data. And that makes it really easy to use. You just write your code to anticipate the kind of data that you get in. So now that we know how to tell the computer to make a noise, we need to figure out how to make the computer make a noise that we want to hear. And this is what the Web Audio API is for. The workflow for the Web Audio API works by connecting nodes together. And you're going to see me write a lot of code, but this is what it boils down to. We take an input, we transform it using different effects, and then we send it out to a destination, which is usually your default system audio out. And we connect these nodes together. And this workflow models the way that a real hardware synthesizer does, where you patch an oscillator into an output in order to make a noise. So let's start with an oscillator and see if we can make an oscillator. This is what oscillators sound like. Oscillators create an electronic signal which make a noise when you connect them to a loudspeaker. So I've hooked up my synthesizer in this video to an oscilloscope so that you can see the shape of this electronic signal and the sound that they make. So a round wave sounds soft. A sawtooth wave sounds sharp. Square wave sounds like a mix of the two. And a pulse wave sounds like, kind of like a sharp square wave. And you could hear me adjusting the pulse width to make it sound sharper. By increasing the frequency or decreasing it, you can play different notes. When you put this all together, you have the foundations of all electronic music. So let's see if we can make an oscillator. So I'm going back to DevTools again. I'm going to increase the size of the window to make it easy to see. And I'm going to go to my oscillator demo. Cool. Right, so like we got the MIDI access for as the gateway to the Web MIDI API, we have something similar concept for the Web Audio API. So we're going to create something called audio context. This is a new audio context. And this is our gateway to the Web Audio API. So like I said, we join different nodes together. What we're going to do is we're going to create a series of nodes that we're going to join together that describe the sound that we want to make. So we're going to create an oscillator node. Oscillator equals new oscillator node. The first thing that we do when we create a new mode is that we're going to pass in the audio context, and that coordinates all the nodes that we're going to make. The second argument that we're passing in is an options object. And one of the things that we can set is the type of wave that we want to create. And we want to create a nice, sharp sawtooth wave. Oscillators by default start making a signal and start making a sound as soon as you start them. Whether you've got a key down on your MIDI controller or not. And of course, as we all know, we want we only want to make a sound when we push a key down, and we want it to stop when we lift a key up. So what we need to do is that we need to create a gate. And to do that, we are going to create a new type of node called a gain node. I'm going to type this, new gain node. We're going to pass in the audio context again, and we're going to set the gain to 0. We use gain nodes to amplify the sound or silence the sound if we want to. And we pass in a gain of 0. We want it to be silenced by default because we don't want it to make a sound just as it is. We only want to make a sound when we push a key down. So we're going to set the gain to 0, and then we're going to start joining our nodes together. So we're going to type oscillator dot connect, and we're going to connect that to the gain node. Then we're going to connect the gain to context.destination. And the destination is by default configured to be our default system audio out. And then we're going to start the oscillator. So next, what we need to do is that we need to open that gate when we push a key down. So we need to write some code that responds to a key down event. So I have this callback here, and we're getting MIDI data passed in, which contains a number of the key that I'm pressing. And I want to set the frequency of the oscillator to the right pitch in hertz. So I'm going to set oscillator dot frequency dot value equal to, I'm going to use a helper function which I created earlier called MIDI to frequency, and that takes MIDI data dot input, which is an integer, and it turns it into a number in hertz of the pitch that I want to play. Next, I'm going to use gain dot linear ramp to value at time, and we want to ramp the gain up to 1, so we'll be able to hear the noise of the oscillator, and we want to ramp it up to a time which is current time plus 0.05 seconds. So I'm going to pop that there. And conversely, when we lift a key up, we want to ramp the value back down to 0. So let's see if this works. I'm going to keep one eye on that. So we can hear the sound of the oscillator now. And if I push a key down, we hear a sound. If I lift the key up, then we get, then it silences it again. Fantastic. So that's oscillators. So let's see if we can turn this into something that's recognizable in the song. See if we can create the bass line next. We need to learn about filters. Filters are a new type of node. They're a new type of component inside a synthesizer, and they're used to quieten, remove, and accentuate certain frequencies of sound. They're often used in electronic music bass lines, and this video shows me patching an oscillator, output of an oscillator, into my filter, and then patching my filter into the output. You should be able to hear that sound get softer and then disappear completely. What it's doing is it's filtering out all the frequencies of sound that are above a certain point. And when I turn the knob down, it decreases the cutoff, the filter cutoff. So it decreases the frequency in hertz above which all the sound is being filtered out. So let's see if we can create a bass line. So we're going back to DevTools, and we are going to go to bass filter. And this code is very similar to the code that we've just written. So we have an oscillator, we have a gain node, which creates a gate. And what we're going to do next is that we're going to create a filter node. So let filter equals new biquad filter node. We're going to pass in the audio context, and we're going to set the frequency to 144 hertz. And that's going to filter all the frequencies from our oscillator above 144 hertz. So if I run this, we should be able to hear a nice, thick, croony bass line. So much, much softer sound. That is a classic electronic music bass line. Next, let's see if we can make the lead melody, which plays the melody in the song. So we're going to learn about something called low frequency oscillators. So low frequency oscillators, or LFOs, are not designed to make noise themselves like other oscillators, but they're designed to automate the changes of the parameters of other sounds. So this video shows me patching an LFO into the pitch component of an oscillator for an accentuated tremolo bass drop effect. What it's going to do is it's going to modulate the pitch. The pitch is going to go up and down slowly at first, and then it's going to get faster as I turn the frequency of the LFO up. What it's doing is it's modulating, it's automating changes to the parameter of another thing. So let's see if we can make this in web audio. So I'm going to go back to Chrome DevTools. I'm going to go back to sources. Okay, and I'm going to go into our demo for the lead. Let's see. Down here. Okay, so we're going to create a low frequency oscillator. And one of the brilliant things about the Web Audio API is that a low frequency oscillator is just an oscillator node like the other ones that we have created. And brilliantly, we can just reuse it and just set a low frequency. So it is literally a normal oscillator with a very low frequency. We're going to set it to 5. We don't want it to oscillate with a frequency of 5 hertz to begin with. And then what we're going to do is we're going to plug it into a gain node. Oscillators by default oscillate between values of 0 and 1. What we want to do is that we want this oscillator to modulate the cutoff frequency of a filter. And if we modulate the cutoff frequency of a filter by just 1 hertz, you're not going to be able to hear the difference. So what we want to do is we want to modulate it by 5,000 hertz. So what we're going to do, we're going to create a new gain node called LFO gain. I'm going to pass in the context. And then we want to pass in the gain of 5,000. So instead of oscillating between 0 and 1, this oscillator, when connected to this gain node, will oscillate between 0 and 5,000. So we're going to connect LFO to LFO gain. Then we're going to connect LFO gain to the filters frequency property. And then we're going to start the LFO oscillator. So let's see if this works. Oh, okay. Connect. I have made my first mistake. There's a typo. Okay, hopefully this will work. You should be able to hear that filter opening and closing about 5 times a second. And if I change my code if I reduce it to just 1 hertz, you should hear that changing much, much slower. Or I can make it faster. And what that's essentially doing is it's just modulating the parameter of something else, and that's what LFOs are for. So that's lead. Okay, samples. Daft Punk didn't actually use samples in around the world. I think a lot of early YouTube videos that analyzed it thought they did, particularly sampling a track called "Good Times" by Chic, but they didn't. They used a synthesizer and they used a drum machine. The drum machine which they used was itself based on samples of real life instruments. They used the Roland TR-909, which was made famous by the acid house, and it was particularly prized for the sound of its cymbals, which were sampled from real life hi-hat and crash cymbals. So let's see if we can get some samples into the Web Audio API. There we go. So the first thing that we're going to do is that we're going to load a file like we do lots of other files. We're going to await fetch, and we want to fetch this file here. And then we want to take that, then we want to take the response, and we want to turn it into an array buffer. And that will put it into an array-like object, which is an array of numbers which describes the sound, the sound waves of that sample. And that's brilliant if you want to mess around with that in code, because that's just a series of numbers that you can mess around with. You can transform it if you know what you're doing. We are just going to leave it as is. And we're going to take the buffer, and we're going to use the audio context to decode audio data from it. Context.decode audio data from the buffer. There we go. So next, we want this function to play our sample whenever I push a key down on the keyboard. So I'm going to write some code to do that. We need to create an audio buffer source node. So source equals new audio buffer source node, and pass in the context. And we're going to pass in the audio buffer as well. Then we need to connect the source node to the destination. And then we're going to start the source node, source.start. One of the pitfalls which I fell into when I was first starting to write this talk and find out about the Web Audio API was that I assumed that you could reuse audio buffer source nodes, that you'd somehow be able to wind them back and play your sample from the beginning. But as far as I know, you can't do that. So on every key press, we are creating a new audio buffer source node and reusing it and then discarding it as soon as this function is finished. I don't think there's any memory leak problems associated with that, but as far as I know, that is how you need to use them. So let's see if we can run this code and see if we can get the sound of a Roland TR-909 clap. Let's see. There we go. That is our sample. That's the sound of a Roland TR-909. Fantastic. Right. Let's see if we could put everything together and see what it sounds like in a complete song. And a quick reminder, while I'm using this MIDI controller to cue the sounds in the browser, it is the browser that is making all the noise that you're going to hear. So let's go back to DevTools, sources, and go down here. And let's hope this works. I'm going to open the console so you'll be able to see all the MIDI data coming in. Here we go. That's it. That's the web audio and the web MIDI API. So how do we sum up? The web audio API requires a bit of domain knowledge to get started. It helps if you know how a real-life hardware synthesizer works, but it's not too hard to get started. Easy things are easy-ish, and hard things are possible. The problem for beginners is it's hard to know which is which often. So what are some of the drawbacks? It's not a digital audio workstation. It's not going to offer you the same kind of power that you get out of Ableton Live or Logic Pro, but it is excellent for education and experimentation, and it's well supported in Chrome, Edge, Safari, and Firefox. The Web MIDI API is well supported in musical hardware. Almost every single piece of professional audio equipment, any kind of sequencer, any kind of synthesizer, whether it's targeted towards beginners or whether it's targeted towards really high-end professionals, all of them will have MIDI ports, either in traditional MIDI or over USB. The only drawback is it's not supported in Safari. It's supported in Firefox, in Chrome, in Edge, but not supported in Safari. But it is excellent for hobbyist development where it is found. So, what does the web do best? Should we be thinking of integrating the web audio API into our websites? Well, no, I'm not going to tell you to do that. I think that's probably a terrible idea. And is it a replacement for serious production tools? Also, no. It's not going to offer you the same kind of power and control and the sheer wealth of audio tools that something like Ableton or Logic will be able to give you. But that doesn't mean that the web audio API and the web MIDI API are worthless. There's a huge community of hobbyists and experimental musicians out there. These people are called circuit benders, and circuit benders make electronic music by using scrap, toys, broken synthesizers to make music out of them. And if they can make music out of rubbish, out of trash, then you can bet that someone will make something cool with a web browser. What makes MIDI so great is that it's used by practically everyone. It's used by amateurs and professionals alike. I knew absolutely nothing about electronic music before I started writing this talk. And that really goes to show how amazing an educational tool web audio and the web MIDI API really can be. The web should be the software platform of the amateur, of the hobbyist, of the auteurs doing something that nobody has ever conceived of before. The web's compatibility, its accessibility, its approachability make it the ideal creative platform. And this is a call for Apple to find a way to support the web MIDI API on iPads and iPhones as well. The web and MIDI belong together. This is Dave Smith. Dave Smith was an engineer and founder of a company called Sequential Circuits. He's also the creator of the Prophet 5, a famous polyphonic synthesizer. Together with the president of Roland, Iketaro Kakahashi, they created MIDI. To this day, MIDI remains completely unlicensed. No fees have ever been created for the creation of MIDI. This has led to its widespread adoption and near universal compatibility. Whole industries and art forms exist because of MIDI, and it remains easy to use for beginners and experts alike. And if that sounds familiar to you, then it should. If you're thinking about the web, then you'd be right. Since its creation, Tim Berners-Lee has not collected any fees for creating the World Wide Web. Free and open standards create wealth for us all. The web has changed our lives for the better. It's critical that the web remains free and easy to use and endures as the software platform for the common good. MIDI and the web are naturally allied to each other and deserve to endure together. Thank you very much.
Thanks so much, Katie. That was fabulous. One of the things that well, first of all, I've loved to do MIDI stuff from back in high school. I got into using all kinds of synthesizers, and it's amazing how, all these decades have passed, and like literally it all just works the same, right? It hasn't really changed, which which goes to show the power of like that, having a standard like that works kind of indefinitely. And you had one of the coolest demos of any talk. you know, uh, I love that song. So really great stuff. I think one of the things you brought up was that I had a question about. Because I've talked about this before when I've brought up web audio API and things like that. Is Well, most of the time the web is kind of outside of videos, right? Like it's quiet, right? You don't go to a website, you don't tend to have audio interactions, but I was making a case years ago that maybe because a lot of other types of software do, you just go to the web and all suddenly you get no audio feedback. Like you're used to like in games and other media where like you click, you know, you'll have audio feedback, and oftentimes that audio feedback is helpful in recognizing like, oh, hey, this was that action because I heard, a different kind of click than I hear from a different action. So, I mean, do you think this is something people should explore and use the web audio API for, or is it like, I mean, what's your feeling on kind of this silence we have across much of web apps interactions?
In general, no, I don't think you should start baking sound and noise into your web apps, and that's for a very good reason. There's a lot of people out there who rely on screen readers to
Yeah.
read out websites, and if you start putting your own sound into your websites, then you're going to disrupt their experience. This is also a very important principle. One of the reasons why you don't have auto playing videos on websites is because if you have auto playing video, then someone who's using a screen reader can't find that video and silence it. So I think perhaps in some very limited circumstances, where you're trying to recreate a specific interface for people who are used to sound in those interfaces, possibly, but in general, no, I wouldn't recommend it for accessibility reasons.
Okay. All right, that makes sense. I mean, I think some sites use it mostly for small things like notification sounds and things like that. Those are, and I've actually, did you use any of the libraries at all, or you just like prefer to use straight web audio API? Because when I've done it before, I've noticed like some of them, for instance, like getting samples and things like that, there are libraries that really make it kind of easy to just drop things in. Um, do you have any you've tried that you recommend, or not really?
Yeah, so the prototype for this talk was written using a library called Tone.js, and I found that to be very helpful. For the demo purposes, I wanted to explore the native web audio API as it is in browsers, but Tone.js is very similar. It has very similar nodes that you can connect together. It works in a very similar way, but it gives you a wealth of other types of nodes that you can connect together. For instance, I think the web audio API and the native web audio API only gives you, I think, a triangle, a sawtooth, a sine wave, and a square wave by default. It doesn't give you pulse waves, which are a really important part of electronic music. But that's something that Tone.js gives you. And for a beginner, I would recommend actually getting started with Tone.js before trying to experiment a bit with the native web audio API. I don't think you're losing anything. I don't think you're losing any less control. It just gives you more toys out of the toy box to play with, and I don't think that's a bad thing. So yeah, definitely go and check out Tone.js.
Awesome. Yeah. Okay. That I don't think I've tried that one. I'm curious. I'll give it a shot. Well, this was great. I love the talk. I love the choice of music and and everything else. So this was really awesome. Thank you, Katie.
You're welcome. Thanks for inviting me.